A new chip just beat quantum computers at their own game, not in a lab demo, not on a toy problem, on the kind of complex optimization work that industries actually care about. So what is this thing? It's called a spintronic chip, and to understand why it's exciting, we need to back up for just a second. A huge chunk of what modern technology needs to do comes down to optimization. You're trying to find the best answer out of an enormous number of possible answers. Which route minimizes delivery time across 1,000 stops? How do you arrange components on a chip to reduce interference? How does a financial model allocate risk across hundreds of variables? These problems get hard fast. As they grow, conventional computers burn more and more time and energy trying to work through all the possibilities. That's exactly why quantum annealers got so much attention. The idea is that a quantum system can explore many possible solutions simultaneously, thanks to superposition. Let the physics do the searching. Companies like D-Wave built entire machines around this concept. And while quantum annealers are genuinely interesting, they've also hit real-world limits. They need extreme cooling, they're sensitive to noise, and their advantage over classical computers has been harder to demonstrate than the hype suggested. Now enter spintronics. This is a different approach entirely. Instead of using quantum superposition, spintronic devices use a property of electrons called spin. Every electron has a spin state. You can think of it loosely like a tiny magnet that can point up or down. In spintronic hardware, networks of these magnetic elements interact with each other. They settle into low-energy configurations naturally, and that settling process is exactly what solving an optimization problem looks like physically. Here's the key insight. Many hard optimization problems can be mapped onto something called an Ising model. That's a physics framework originally used to study magnets. In an Ising model, you have a bunch of variables that interact with each other, and you're trying to find the configuration that minimizes the total energy. A spintronic chip does that literally. It's not simulating the physics. It is the physics. The hardware itself is the solver. What researchers found is that spintronic networks can find those low-energy solutions faster than tested quantum annealers, and they do it while consuming far less power. That's a significant combination. Speed matters for real-time applications. Energy consumption matters at scale. And unlike quantum annealers, spintronic devices don't need to be cooled anywhere near absolute zero. They can operate closer to room temperature, which is a massive practical advantage. Now, this doesn't mean spintronics is simple. Engineering these networks is genuinely hard. You need precise control over how the magnetic elements are arranged and how they interact. The connections between them encode the structure of the problem you're trying to solve. Getting that mapping right and building hardware that stays reliable is serious materials science and engineering. But the physics is on your side in a way that's encouraging. Magnetic systems want to find their lowest energy state. That's just what they do. You're not fighting the physics, you're harnessing it. And because the computation is happening through physical dynamics rather than billions of logic gate operations, the energy cost can be dramatically lower. The applications here are broad. Logistics companies trying to optimize routing for fleets, telecom networks optimizing signal allocation, AI training pipelines that need to solve scheduling or resource problems, drug discovery workflows modeling molecular interactions. Chip designers trying to minimize power and latency at the layout stage. These are all domains where optimization is a constant, expensive bottleneck. What makes this moment feel significant is that it's not just a theoretical result. The spintronic hardware was benchmarked directly against quantum annealers on real problem types, and it came out ahead. That's the kind of head-to-head comparison that shifts how researchers and engineers think about which technology to pursue. It's also worth thinking about where this fits in the broader computing landscape. We're not talking about replacing general-purpose processors. Spintronic chips aren't going to run your operating system or render video. They're specialized hardware built for a specific class of problems. But that class of problems is enormous and growing. As AI systems get more complex, as logistics networks scale, as chip design gets harder, the demand for fast, efficient optimization only goes up. Quantum computing isn't dead. Quantum annealers are one slice of that field, and there are other quantum approaches with different strengths. But the spintronic results suggest that the path to better optimization hardware might not require the extreme complexity of quantum systems. Sometimes the most elegant solution uses physics in a more direct way. This is still early. Spintronic hardware at scale, with programmable problem mappings and robust manufacturing, is still a research challenge. But the core result is clear. Electron spin, managed through smart materials engineering, can solve hard problems quickly and cheaply. That's a foundation worth building on. The next few years will be interesting. We might look back at this as the moment a quieter technology stepped out of the physics lab and into the conversation about what computing looks like next.